Hello, everyone. This is the second video on sampling distributions for my Camden County College students. This is for section 5.4 of your textbook. And we'll do a quick review of what we covered last time, and then we're going to do some problem solving today. And so let's get right to it. And we'll get right to the, we'll do a screen share here first. And we'll go ahead and show you the textbook. So let's start the screen share. There we go. And let's get right to our textbook. Here we go. This is on page 263 of the textbook. Last time I described what a sampling distribution is, which is a list of all the possible samples of size n. And basically what you do for each of the samples is you find the mean of each of the samples, and then you'll have a list of sample means. There could be thousands of these sample means, or maybe millions of them. Then we take the mean of all these sample means, we average all of them, we get what's called the mean of the sampling distribution. And as you can see on page 263, it mentions it right here, where mu x bar is the mean of the sampling distribution. What we find is that's equal to the mean of the population. That's mathematically always true, right? Always true. Doesn't matter what the sample size is. Down here, we find that as long as the sample is small compared to the population, a very good approximation of the standard deviation of the sampling distribution of sample means is equal to this ratio right here, which is in the numerator, it's the standard deviation of the population divided by the square root of the sample size, right? Now, what the central limit theorem says is if we know nothing about the population, we don't know if it's normal or skewed, if the sample size is large enough, that is at least 30, then even though the population may not be normal, the sampling distribution itself, sample means, is considered to be approximately normal. So that's important so that we can use normal CDF in answering questions about the probability of a sampling of a sample. Now, if we know that the population, this is point number 2 here, if we know that the population is normally distributed, then the sampling distribution of sample means is automatically considered to be normally distributed for any sample size. It doesn't have to be greater than 30, right? That's what we were talking about last time with the central limit theorem. We're going to make use of that and solve some problems today. All right, so let's go to the next couple pages. I think I went through some of this last time. Basically comparing, well, actually, let's go through this problem here. I don't think we did this last time. It says a study analyzed the sleep habits of college students. The study found that the mean sleep time was 6.8 hours, the standard deviation of 1.4 hours. So we'll consider those two to be population parameters. That is, the population mean sleep time is 6.8, that's mu. And the standard deviation sleep time is 1.48 hours, that's sigma. That's for the population. It says here random samples of 100 sleep times are drawn from this population. So that means n, small n, the sample size is equal to 100. And the mean of each sample is determined. Find the mean and standard deviation of the sampling distribution of sample means. Well, suppose this is this unusual shape here is the shape or distribution of the population of sleep times. It's definitely not normal looking. It looks like it's skewed to the right, or what we can call positively skewed to the right. So what can we say about samples of size 100? Well, number one, we know that the mean, excuse me, let me just pull this back up. We know that the mean of the sampling distribution of sample means is going to be equal to the mean of the population, which, as I showed you here, it's 6.8. So we know what the mean of the sampling distributions are, the x bars. 6.8. Standard deviation is going to be equal to the standard deviation of the sample means. It's going to be equal to the standard deviation of the population divided by the square root of n. Right, sigma is 1.4 hours. That's our numerator. And our sample size, as it says up here, is 100. That's our denominator, square root of 100. So 1.4 divided by the square root of 100 is 0.14. That's the standard deviation of the sampling distribution. We also call that the sample error. I'm going to refer to sample error from now on. That means the standard deviation of the sampling distribution of sample means. Okay, so there we go. There's our mean and there's our standard deviation. And because the sample size is 100, you can assume that the distribution of the sample means, the distribution of sample means, the sampling distribution is going to be approximately normal. You will have the 6.8 mean, which is right in the middle here, but it will have a much narrower standard deviation. It's 0.14, as opposed to a much wider one for the population, which is 1.4. Okay. And since, again, n is greater than 30, we can consider this to be approximately normal. And we can use this normality to answer probability questions. Even though the original population, certainly can't use normal CDF for this, it's not normal. But we can certainly use normal CDF for this sampling distribution because it is normal. Okay. Let's go to the next page. All right. And this is another example. I think maybe this is the one we might have done last time, but we'll look at it again. If not, we'll no problem looking at it again. It says, assume that the training heart rates of all 20-year-old athletes are normally distributed. So we're assuming now the population is normally distributed. Great. Doesn't matter what the sample size is here. The sampling distribution is going to be normal. All right, anyway, the mean of the populations is 135 beats per minute. That's the training heart rate for 20-year-old athletes. And so that's mu. And sigma, the population standard deviation, is 18 beats per minute. And this is what the population distribution looks like, 135 in the middle here. All right, so this is the population curve, and we'll assume that the sampling distribution is also normal. Random samples of size 4. Notice it's much less than 30, but we don't need 30 if we know the population is normal. Population is normal, the sampling distribution is automatically normal. Sample size could be very small, like 4. Okay, so anyway, we can answer. We can use normal CDF in this case here. So what is the mean of the sampling distribution of sample means? It's equal to the mean of the population, which is 135 beats per minute. What is the standard deviation of the sampling distribution, or what we call the standard error? It's equal to sigma, which is 18, divided by the square root of n, which is 4. Square root of n, square root of 4 is 2. 18 divided by 2 is 9 beats per minute. That is the standard error for the sampling distribution. And then we just drew it just like that. All right, so we're going to get pretty close to doing our examples in a minute. I think maybe this is the one we did last time. I believe we did this one last time. But anyway, I just wanted to show you, if you wanted to convert your mean score, mean statistic, to a z-score, all right? You take your mean, the actual sample mean, you subtract out the mean of the sampling distribution, which happens to be the mean of the population, same thing, and divide it by the standard error. Remember the standard error? That's the standard deviation of the sampling distribution, which is equal to the population standard deviation divided by the square root of n. So this division here, the standard deviation divided by the square root of n, is in the denominator of the z-score, all right? This whole thing here is in the denominator. I'm going to make that clear to you. So anyway, here's an example of doing a probability problem. Now, in this particular case here, where we can use, instead of doing what they're doing here, we can just use our calculator, normal CDF. Right? So anyway, I'm just going to put a pen ready here and write down this information. It says that the figure at the right shows the mean distances traveled by drivers each day. You randomly select 50 drivers. That's our sample size. So n is equal to 50. All right, 50. So you randomly select 50 drivers ages 16 to 19. Now, they're referring, obviously, to this group right here. There's a bunch of age groups here. We're going to ignore these 4 age groups, and we're going to strictly look at this age group right here, ages 16 to 19. What is the probability the mean distance traveled each day is between 19.4 and 22.5 miles? So that's the mean of these 50 drivers. You randomly select 50 drivers. You haven't measured their mean, the miles that they drove that day or traveled that day. We're going to ask what's the probability that when we do measure it, it's somewhere between 19.4 and 22.5 miles. That's the mean, not one person, the mean of 50 drivers. Okay, that's what we're asking. Assuming the population standard deviation is 6.5 miles. So we're going to use from you 20.7 miles in a day, because that's for the 16 and 19 age group. This is it right here. That's our population. So consider the age group 16 and 19 to be our population. 20.7 miles is the mean. Sigma for all these age groups is 6.5 miles. That's what CDF here. Regardless of the age group, that's our standard deviation. So anyway, the mean of the sampling distribution is going to be equal to the mean of the population, 20.7 miles. That's this number here. The sampling distribution standard deviation, or the standard error, which is equal to the population standard deviation, divided by the square root of the sample size, is 6.5. That's this number, divided by the square root of 50. That's the number of drivers. Okay? And that's approximately 0.9. Now, here's the deal. We don't have to actually calculate the standard error here. We can use this in our calculator, as I'll show you in a minute. So I'm just jotting down some of these things. And we want to know what's the probability that the mean of the 50 drivers is going to be between 19.4 and 22.5 miles. So what we're going to do is go to answer this question. We're going to go right to normal C to our calculator, and we're going to hit second VARS, scroll down 1 to normal CDF. If you have the 83 calculator, remember it'll open up a set of parentheses. You have to put these 4 numbers in this order: lower limit, upper limit, mean, and standard deviation. Now, what is the lower limit? Well, it says from 19.4 miles, so we're going to type in 19.4. And then the upper limit is going to be 22.5 miles. That's what it says. And then the mean is going to be 20.7. Now, be very careful here. What are we going to put in for sigma here? Now, sigma is referring to the standard deviation, in this case, of the sampling distribution, not of the population. So we have to put in 6.5, the population standard deviation, divided by the square root. The square root, that's how we find the square root of 50. Close parentheses. Scroll down. Hit enter. That's the order that you should be seeing when you entered it into your 83 calculator. Hit enter. Oh, that's your probability. 0.8962, approximate number there. 0.8962. Let's go back to the textbook. Where are you? There you go. Now, what did they do in the textbook? Well, they didn't use the technology. They used tables. They converted each of these endpoints of the interval. The 19.4 and the 22.5, they converted them into Z's using which formula? Well, with that formula on the top of the page here, this formula here. That's what they did. All right, so now we have z-scores for each of those endpoints. And so this probability here is equal to this probability using z's. And then they subtracted these two probabilities to get 0.8957. Now, why is it my answer 0.8962 and theirs 0.8957? It has to do with the fact that my answer is more precise with your calculator, much more precise. They're using tables here. Tables are not as precise as the, and also up here, if you could see, I shouldn't say the table's not precise. What I should be saying is that these z-scores are approximate. So we rounded them to 2 decimal places. The calculator doesn't do this rounding. It converts the actual miles driven, the 19.5 and the 22.5, to the z's and leaves all the decimal points, and they don't round at this point here. So this is really a rounding issue. 0.8962 that we got with the calculator is a better answer. All right. What's the interpretation? Of all samples of 50 drivers ages 16 to 19, about 90% will drive a mean distance each day between 19.4 and 22.5 miles. Of all samples of 50 drivers ages 16 to 19, 90% of what? Of those samples will have mean driving distances of those 50 people in each sample. 90% of those samples will have mean driving distances between 19.4 and 22.5 miles, about 90. And to be more precise, 89.6 or 89, yeah, 89.6% chance, or 89.6%. All right. Let's now go to this next page here. All right. And here's another example of the same type of thing. The mean room and board expense per year at 4 years colleges. This is our mean. Now, you randomly select 9 colleges. Well, wait a minute. 9 is much less than 30. Well, do we have to assume something? Yes. We have to assume that room and board expenses are normally distributed. That's the population's normally distributed. Otherwise, we can't use normal CDF. We can't use the central limit theorem because we're only selecting 9 colleges. That's our sample size, 9. So we had a opportunity here to look at the population, and we see it's normally distributed, so we're good. So let's read it again. Mean room and board expense per year for your colleges is 10,453. That's our U. N is 9. That's the number of colleges selected. What is the probability that the mean room and board, that's the mean. We selected a sample of 9 colleges. What's the probability that the mean of those 9 colleges for room and board is less than 10,750? Assume that room and board expenses normally distributed with a standard deviation of 1650. That is our sigma. That's our population standard deviation. So we're going to write down our sampling distribution since and we have to assume here because the population is normally distributed. What can we say? The sampling distribution is normally distributed regardless of the size of the sample. Sample's 9. It doesn't matter if it's greater than 30. It's definitely normal here because the population is normal. U x bar, the mean of the sampling distribution, is equal to the mean of the population, 10,453. The standard error, which is the standard deviation of the sampling distribution, is population standard deviation divided by the square root of the sample size, 1650 divided by the square root of 9, which is 550. Okay. Now, do you have to convert 550 into a z? Or excuse me, what is the question? Oh, yes. What is the probability that the mean room and board is less than 10,750? Do you have to convert the 10,750 into a z? No, because our calculator will do it for us. We're going to do this problem using our calculator. So the mean is 10,453, and the standard error is going to be 550. We don't use 1650, we're going to use 550. We want to know what's the probability that X bar is less than 10,000. Probability here. Let's go back to our calculator. Again, we'll do normal CDF. Now, enter. And in this case, if the probability X bar is less than, so we have to have a lower limit, a much smaller lower limit. If we're dealing with numbers here that are into tens of thousands of dollars, let's make the lower limit -1 million, just to be safe. Open 6 zeros after the 1, -1 million. And then the upper limit is going to be our 10,000, what is it, 750. Okay. Our mean of the sampling distribution is again 10,453. 10,453, here we go. And our standard error, standard deviation of the sampling distribution in this case, is going to be 550. We already divided out the square root of n into this problem. Enter. This is what, again, what it would look like inside your parentheses for your 83 calculator. And oops, looks like I got an error, so I must have done something wrong. Oh, I know what I did wrong. So you caught it. You were screaming at the video saying, "Professor Parrish, what's wrong with you?" Well, I put a negative. I put a minus sign here. It should be a negative sign, right? Always get an error message when you do that. So there we go. Hit enter this time, and we got our correct answer. So sometimes it's good to show some errors so that you remember put the minus sign there, not the, excuse me, put the negative sign there, not the minus sign. 0.7054 is our answer. Probability. So let's get back to the book. And there it is. You see, they actually did the calculation with the TI-84. And now, if we did, if we set the probability of Z is less than 0.54 after we converted 10,750 into the Z, we would get exactly the same answer, 0.7054. All right, so there you go. All right, so it says about 71% of samples of size N will have a mean less than 10,750. And it also means, interestingly, that 29% of these means will be greater than 10,750, right? Absolutely. 71% is less, 29% must be more. 71% plus 29% is 100%. All right. And finally, the last thing we'll do before we look at some examples is to make the distinction between probabilities for populations and probabilities for samples. All right. So finding probabilities for X and probabilities for X bar using the normal CDF. Let's see the difference between the two. Let's look at this problem, and then we'll see how they set up the problem, and that's all we'll do for now. And you can actually work this out yourself with your TI-83, 84 calculator. So it says here, some college students use credit cards to pay for school-related expenses. For this population, the amount paid is normally distributed. All right, good. So we'll assume the sampling distribution is normally distributed. The mean of the population is 1615, and the standard deviation is 550. All right. So these are population parameters mu and sigma. Let's look at number one. What is the probability that a randomly selected college student who uses a credit card to pay for school-related expenses paid less than $1,400? And now we're not dealing with samples anymore. We're dealing with one student. This is X. This is X now. This is a random variable X. This is for one student, not a sample of students. So what is the probability going to look like? Right down here. It's the probability that X is less than 1,400. That's what we're trying to find now. And when we use normal CDF for this, right, our mean is going to be what? 1615. But what are we going to use for the standard deviation inside normal CDF? but you want to use just 550. We're going to use the population standard deviation to answer this question because this question is only about one person in the population. All right? This is where we would use the population mean and the population standard deviation inside normal CDF. All right? Just picture in your mind, normal CDF, what's the lower limit? Negative 10,000 maybe. What's the upper limit? 1,400. What's your mean? 1615. What is the standard deviation that you enter into your calculator? 550. When you do that, you're going to get this approximately this answer here, 0.33483, maybe slightly different depending on whether you use technology or not. All right. Now, how about the second question? It's a different question. You're randomly selecting 25 college students who use credit cards to pay for school-related expenses. What's the probability that their mean amount paid is less than $1,400? In this case, you find the mean amount paid for credit cards expenses, for school-related expenses, for the 25 students. In other words, you ask each of the 25 students, how much did you pay for school-related expenses using your credit cards? They would all give an answer. You would then find the average or mean of those 25 answers, and that's X bar. What are they asking here? What's the probability that X bar, the mean of the 25 students, the mean amount paid by the 25 students is less than 1,400? It's a different question. Part one is asking about one student. What's the probability that one student paid less than 1,400? Question two is asking, what's the probability that the mean of the 25 students is less than 1,400? And you're going to get a different answer. In number two, it's the probability that X bar is less than 1,400. X bar, not X. Okay? When you put it into normal CDF, the mean is going to look the same, but the standard deviation, what you're going to enter is what? You're going to enter the standard deviation. What was it again? What did we say it was? 550 before? Yeah, 550 is the standard deviation. We're going to enter 550 divided by the square root of 25, which is the sample size. 550 divided by the square root of 25. This number right here, this ratio right here, 550 divided by square root of 25, that's what you enter into normal CDF when it asks for the standard deviation. It's a standard deviation of the sampling distribution. We're going to use the sampling distribution mean and standard deviation to answer question number 2. I hope you see the distinction between those two types of probability questions. All right, now, what we're going to do now is spend about 10 minutes to answer some questions here in your textbook, in the back of your textbook itself. I have posted, by the way, 5.4 in my math lab, so you can start working on that. I know there were some issues with my math lab in the last few days, but it seems to be working just fine today. So it is posted. You can go ahead and do the homework. And also, by the way, the due dates for all homework starting with 5.4 will be May the 8th. So I'm not putting any deadline until May the 8th, but May the 8th is the final deadline for all homework. All right, so don't wait to the last minute to do homework, and please do not ask me for any extensions beyond May 8th. I will not give you any, none. And there's plenty of time, right? Between now and May 8th, you got over a month to complete, I think it's 5 weeks now, 5 weeks to complete all the homework. So no extensions beyond May the 8th, plenty of time. All right, so let's look at questions 5 through 8. These are true-false questions based on what we learned over the last 2 sessions. I hope you can answer them, but we'll go through them now. And I have written down the answers to these questions, and I will show you the answers in a second. But let's look at number 5, question 5 here. As a sample, and we're supposed to just say, is it true or not true, true or false? As the sample size increases, the mean of the distribution of sample means increases. Just think about that for a minute. Is it true or false? Number 6, as the sample size increases, the standard deviation of the distribution of sample means increases. True or false? Number 7, A sampling distribution is normal only when the population is normal. Is that true or is it false? All right, think about central limit theorem. And number 8, if the sample size is at least 30, then you can use z-scores to determine the probability that a sample mean falls in a given interval of the sampling distribution. So you would convert your x bars to z's. That's what they're really saying. Can you do that? If the sample size is at least 30, you can use z's, which are used for what? The standard normal. Is that true or false? Well, let's look at the answers. So we have answers here for you. All right, number 5. The mean of the sampling distribution, this is a false statement. The mean of the sampling distribution is always equal to the population mean, regardless of the sample size. So it doesn't matter if the sample size is increasing. The mean of the sampling distribution is always equal to the mean of the population. Period. So that's false. It doesn't change. It doesn't increase. Number 6. This is also false. As the sample size increases, the standard deviation of the sampling distribution, which is, of course is called the sampling, the standard error, it should be decreasing, not increasing. And why? Because here is the standard deviation of the sampling distribution is equal to the standard deviation of the population divided by the square root of the sample size. As n increases, the denominator increases, doesn't it? If the numerator stays the same and the denominator increases, this whole ratio decreases. So the standard error, or another way of saying the standard error, standard deviation of the sampling distribution must decrease as the sample size increases. So that was false also because it said it would increase, not decrease. Number 7, this is also false. It said something like the sampling distribution is only normal when the population is normal. No. The central limit theorem says that if the population distribution is unknown or known to be skewed, the sampling distribution is approximately normal if the sample size is at least 30. So it is true that the sampling distribution is normal if the population distribution is normal at any sample size. That's true, but it's not the only way the sampling distribution is normal. It could be also normal when the population distribution is skewed or unknown, but the sample size is at least 30. The central limit theorem says then you can use the normal distribution for the sampling distribution. The only true statement is number 8. Number 8. What was number 8 again? Look at number 8. If the sample size is at least 30, then you can, yes, of course. This is what we just said. It's number 7. All right. You can use the normal distribution. The sampling distribution is normal. Absolutely. 8 is true. All right. Now let's look at number 15 on the next page. Or actually, is it on this page? No, next page. Number 15. Let's take a quick look at it. Again, I'm going to post later tonight these solutions so you can see them. All right. So in these cases here, you're supposed to find number 15. We're only going to do 15, by the way. You can try these others if you want. You're given the population mean and standard deviation, and you're given the sample size. Find the probability of a sample mean being, in this case, less than 24.3. Less than 24.3. All right. So, and they say the mean is 24. The population mean 24. The population standard deviation is 1.25. So let's go ahead and look at our solution. You can try this on your own with your calculator. What we're being asked to find is the probability that X bar, the sample mean, 64 people, is less than 24.3. It's probably the mean of 64 people is less than 24.3. Here's the mean of the population, 24. Standard deviation 1.25. Now it says nothing about normality of the population, right? Nothing's being said about that. But The sample size is 64. It's bigger than 30. According to the central limit theorem, sampling distribution is approximately normal. So the probability X bar is less than 24.3. We can use normal CDF to answer this question. The less than here indicates that we would want a very small negative number here on your lower endpoint, like negative 1,000. The upper endpoint is 24.3. The mean is 24, but look, since we're finding the probability of X bar, we must use 1.25 divided by the square root of the sample size, which is 64. Don't forget about dividing by the square root of 64 because we're dealing with a sample, not an individual. 0.9735. Now it's asking if this is unusual. In general, in statistics, if a probability is less than 0.05, we'll consider it to be unusual. In this case, 0.9735 is much larger than 0.05. This is not an unusual probability. Not an unusual event occurring when we assume that the mean is 24. All right, mean of the population is 24. Not unusual to see a sample mean of 24.3. All right, now we're going to go to our textbook and we're going to look at page 270, number 17. All right, page 270, number 17. I guess we are doing this one here, number 17. All right, so let's look at that one. In this case, n is 45. The probability of the sample mean being greater than 551 when the population mean is 550, standard deviation is 3.7. This is a greater than problem here, but we're dealing again with a sample mean. So let's look at the solution for this one. So we're being asked to find the probability that X bar is greater than 551, and the sample size is 45. The mean is 550 for the population. The standard deviation of the population is 3.7. Once again, since 45 is greater than or equal to 30, the central limits theorem says the sampling distribution is approximately normal. It has a mean of 550 and has a standard error of 3.7 divided by the square root of 45, all right? And that's what we put into our calculator. Now, notice that you don't have to estimate your standard error. You can simply put it in as 3.7, sorry about that, 3.7 divided by the square root of the sample size, 3.7 being the population standard deviation. Notice the answer is 0.0349. This is considered unusual. In other words, if the population is actually 550, and you want to know what's the probability of getting at least 551, and the answer is a little over almost 3.5%, that's considered unusual because anything under 5%, 0.05, is considered unusual. So there's a small chance that if the mean is 550, it's a small chance that you would get 551 or higher, about a 3.5% chance. And then we're going to look at the last, I think we have a couple more. Yeah, this is the last one. This is page 272, number 35. So we're going to look at that, and then we'll end our meeting today. So we'll go to the next page, and then the next page over, page 272, and we're going to scroll down to number 35. It's more of a word problem. It's a typical type word problem for sampling distributions. All right, so suppose we are in a manufacturing plant. It says a machine is set to fill paint cans with a mean of 128 ounces. So that's what's printed on the can, 128 ounces. Now, as you probably know, some cans will have a little bit less than 128. Some cans will have a little bit more than 128. But the paint can says it should be 128 ounces. Standard deviation, not much of a standard deviation, 0.2 ounce. So what does the manufacturing plant do? They take a random sample of 40 cans. Maybe they have 1,000 cans they produce a day. So they take a random sample of 40 of them. And suppose the random sample has a mean of 127.9. Now, notice it's below 128 ounces, right? It says here the machine needs to be reset when the mean of a random sample is unusual. What is unusual? Less than 5%, let's say. Let's make that to be the criteria. And the probability of that mean occurring is 5%, right? Does the machine need to be reset in this case when we actually get a sample mean of 127.9? So let's see how to do this problem. Here's our mean, 120, this population means 128. That's what should be in the can, right? 128 ounces of paint. Standard deviation is 0.2 ounce of paint. We take a sample of 40 cans on a day. And on one particular day, we got a sample mean of 127.9. Now, since 127.9 is less than 128, what we're going to do when we set up the probability is that we'll say, what's the probability that X bar, the sample mean, is 127.9 or less? All right, get the idea? Or more extreme or further away than 127.9. Since 127.9 is less than 128, we're going to say less than or equal to 127.9. I hope you get that idea. That because it's less than, we're saying anything that is 127.9 or less than that is what we're calculating. And if we find that it's less than 0.05, then the machine would be reset. All right, so how do we do it? Once again, since the sample is 40, and we had 40 cans, and then it's bigger than 30, we're going to assume that the sampling distribution is normally distributed. And what does the sampling distribution mean? Equals to the population mean of 128. The standard error, notice, for the sampling distribution is 0.2, the population standard deviation, divided by the square root of the sample size, which is 40. All right? And we don't even have to figure out what that number is. We can just simply put that into our calculator. Since the sampling distribution is approximately normally distributed, we'll use normal CDF. And it's less than or equal, doesn't matter. We're going to put negative 1,000. In this case, because the numbers are bigger, we're going to use negative 10,000 for a lower limit. 127.9 is our upper limit. 128 is our mean of the sampling distribution, and this is our standard error. I just type it in that way. Now, if you do this with your calculator, this is what you get. I don't know if you remember in class we went over something like this. Some students, when they see, sorry about that. There you go. When they see this, they think the probability is 7.827. No, the E here means exponent. That means 10 to the negative 4 power. That's what this means. So I'm rounding it to 3 decimal places here. 7.828 times 10 to the minus 4 power. What the minus 4 power says is take that decimal point and move it to the left by 4 places. And when you do that, you're going to get 0.00078. That's a really small probability. That's a 0.078% chance. That's much lower than 0.05. All right? So if you end up with this 127.9, that's considered extremely unusual. Extremely unusual. And therefore, the machine needs to be reset. In other words, the manufacturing process, filling of the can process has to stop, and they have to do some sort of work on the machine. This is unacceptable. 127.9, extremely rare for that to happen. There's something wrong with the machine. The machine is not filling the cans correctly, and that's what the result is here. All right, anyway, that is it for today. I hope you got something out of this lesson. And I will post both the video tonight, which is Friday night, April 3rd, and also post the solutions that I just showed you, this PDF of solutions. I'll post that also in Canvas, and it will be posted, I believe. I will put in the posting in pages, I think. Most likely under pages. That's where I'll end up posting it. But I'll send out an email tonight. All right, anyway, that's it. And have a very nice weekend. And remember, Saturday is my day off. So please If you can, refrain from sending me emails, unless, of course, a couple of you, one or two of you, need to take your exam because you had some issues, emergency issues. Then, of course, I will be checking the email for your but for everyone else, I'll be looking at emails again on Sunday. All right, so tomorrow, Saturday, April 4th will be my day off. All right, and again, have a very nice weekend. Stay healthy, stay safe, and I'll see you again next week.